Hello. Um, so in this lecture, we are talking about temperatures. So the topic will cover the temperature and the zero law of the thermodynamics, the thermal expansions, and the macroscopic description of the ideal gas. Okay. I'm sorry that if video is have a delay. I'm trying my best. So this week I plan that we're gonna finish this topic and then the kinetic theory of gas and then the first law of the thermodynamics. So next week we're gonna have one remaining topic, which is the second law of the thermodynamics, and then the review before the exams. Okay, I'm doing my best that we can uh, finish everything on times, and the exam's gonna be on the Friday of the 23rd of July. Okay. I'm not sure about the first three video. I think one of them maybe have the issue with the sounds. I'm not sure. It's like on and off. It's low and quiet at some point. If you have any questions or something that maybe you missed from the video, just feel free to ask. Okay, during the review sessions or sending by emails as written on the slide. Okay, I will answer that. Okay, so this video is gonna be short. I'm not sure how long. It's maybe half an hour, 45 minutes, just to finish this one. Okay, let's start. What is the temperatures? It seems to be a normal word, but it's maybe hardly described on what exactly it is, right? Because you can feel it. For example, if you touch something hot, you feel that it's hot because it's you said that because it's a higher temperature than your body, for example, so you can feel that. Okay. So basically, the temperature is it's the quantities. Okay, it's a quantity that tell that it's hot or it's cold. Okay, the process is the heat transfer. Okay, it's coming from the process of the heat transfer. So when it's you touch something hot, the heat is transferred from that hot object to you, and so you can feel that. So when you say this hot and cold, so you need a reference, right? You need, let's say, for example, if you touch something hot and you say that it's hot because it's hotter with respect to you. Okay, it's maybe not hotter with respect to something else. For example, if you the hot tea and what to say the light bulb, for example. So it's not hotter than a light bulb. It's colder. Okay, so you need some kind of the reference. Okay, so the instrument that we normally use, it's called to measure the temperature, is called the thermometers. Okay, which normally it's made from the mercury. Okay, in the past, so we have the mercury temperatures that I think maybe you are familiar with that, or you see that in the daily life. Okay, and you can see that the temperature it's very important for us. Okay, as you know, for example, you use it as a one indicator of the COVID situations. And if you're looking in the infrastructures like the building, the roads, you need to also consider that the material can be expand or extract when the temperature change. Okay, so you need a higher and you need the engineering design to also support this kind of thing. Okay, so what is the zero law of the thermodynamics? Okay, so the law is just quite simple. So if you have an object A and B separately in a thermal equilibriums, and then the object C, A and B are separate in a thermal equilibrium with the third object, which is C. So if it's in that case, A and B are in a thermal equilibrium with each other. Okay. In the figure, for example, you have the object A and another system. It's the temperature measurements, the thermometers, which is C. Okay, and then you have the object B with the same temperatures. So when you attach A and B together, there are no heat transfer. Okay, so nothing is moving and no energy will be exchanged between A and B. So it's, you say that A and B are in a thermal equilibrium to each other. Okay, so this law is important because it's enable us to define the temperatures. Okay, so you have the reference scales somehow, and then so when you use that temperature to measure your bodies, and then you measure the temperature of your friends' bodies, okay, your family bodies, and then if it's equal, so it means that when you touch each other's, you will not feel that he or she will is colder or hotter than you. Okay, because there are no temperature exchange. Okay, so this is the zero law of the thermodynamics. Okay, just a second. Okay, so before we go next, I would like to discuss first about the thermal expansion. It's a short topics, but sometimes it's the exam come with a very short questions, for examples. So when the temperature change, so for example, these figures, the length between the molecules can change. Okay, so at the result, your material, it's the length is different. So as you see from the example of in this figure, so the bridge expansions. Okay, so we define the average coefficient of the linear expansions. The alpha is defined by the length that it's expanding divided by the original length, the initial length, and then divided by the difference of the temperatures. Okay, so the alpha have the units of per temperatures. Okay, so it's per Kelvin, for example, or per degree centigrade, whatever. Okay, so it's just a unit of the temperatures. Okay, yeah, I think people measure it in per degree centigrades. Okay, which is fine. Okay, or you can write the formula as the delta L equal to the alpha, the original length, and the delta T. Okay, so in this case you can calculate. For example, if the problem asking what is the length difference in the aluminum, so you're just looking in the table, looking for the aluminums, looking for the coefficient, put it here, what is the original length, and then what is the change of the temperatures. Okay, so one thing that I would like to let you try to do it by yourself. Okay, it's on the book, it's in the book. I think survey should already mention about that. Okay, so let's say this is your homework. Normally, and now I'm talking about the one-dimension expansions or contractions. So what if we would like to consider the surface and the volume expansions? Okay, it's gonna be the same alpha. It's gonna be 2 or 3 alpha. It's gonna be alpha square or the alpha to the cube. So this is the homework. Okay, so let's try to do it by yourself. Okay, it needs some small approximations. Okay, but I think that the survey already mentioned that and described that well already. Okay, So this is one small example. So we have a segment of the steel railroad track that have length of 30 meters when the temperature is 0 degrees centigrade. So what is the length when the temperature is the 40 degrees centigrade? Okay, so this is simple. You can start with the delta L, which is equal to the alpha, the original length, and the delta T. Okay, so this is steel. Looking back, the steel is 11 to the -6, I guess. Okay, let's put it in this way. And the unit is 1 per degree centigrade. Okay, the length it's 30 meters. Okay, and the delta T is equal to the 40, okay, which is the degree centigrade, so that you get the answer. Okay, and what you get if you answer it immediately, it's gonna be fail, and it's not the proper answer, because what you get is the delta L. Okay, so the answer needs to be L, which is 30 meters plus the delta L. Okay, so this is the proper answer. Okay, some people just, okay, you calculate this one and you use it to the you just write it to the answer sheet. This is not correct. Okay, just be careful. And then when you do everything, just make sure that you are doing in the proper units. Okay, so if you're looking in this on the right side of the equations, you can see that one is a degree centigrade, one is the inverse of degree centigrade, so it's cancelled. So the unit is basically meters in this case. Okay, so this is the benefit if when you try to calculate something, just also do the dimension analysis for that, so you know that you use at least the first order corrections that you check. Okay, that the unit or the answer is the right thing. Okay, so we go next back to the temperatures. So we are talking about the absolute temperature scales. Okay, so the instrument that we're using is called the gas thermometer. Okay, which is the constant volume apparatus. So this is how the gas thermometer look like. Okay, so you have the gas in the flex, which is keep constant by raising or lowering the reservoir, and then you have the scales here. Okay, and you have the mercury reservoirs here. Okay, so the basically what you are trying to do is that you try to lower and raising these reservoirs, okay, to keep the scale as the constants. Okay, so this is what we how the principle of this apparatus works. Okay, and then you try to plot between the pressures and the temperatures. Okay, so this is for 3 trials. So so you measure the trial ones. Okay, so it can be the gas with the gas sample ones, for example. So you plot between P and T, between P and T. Then you have for 3 samples. So in this case, when the experiment happen, and then you can extrapolate, okay, the plot, because you cannot working in a very low temperatures, or okay, So if you do extrapolate to the plot will meet at one point. So that point is corresponding to the 273 degree centigrades, the -1. Okay, so in that what we call it the absolute zeros. Okay, so when the pressure becomes zeros, the temperature is um, these at these temperatures. Okay, so this is what we define. So the Tc equal to T minus 273.15. Okay, and this is the absolute zero of the what we call it the 0 Kelvin. Okay, which is mean that the gas, we don't have any pressures at that temperature. Everything stops, no interaction between gases. Okay, and this is the definition of the absolute zeros. Maybe I just make the note before we move. Just so that you can have more explanation on the slide. Okay, so it's a thermometer that measures temperatures by the variations in volume or pressures of the gas. Okay. Sorry, I should write it in the beginning, but I forget about that. So just putting some description so that you have more explanations. Okay, and this following the Gay-Lussac's laws that we will discuss later. Okay, so this is about the absolute temperature scales. We go to the examples. Okay, in the experiments, the constant volume gas thermometer is calibrated in a dry ice, which is minus 78.5 degrees centigrades, and in the boiling ethyl alcohol, which is 78 degrees centigrades. Okay, the separation pressures are 0.9 and 1.635 atm. So the question is, what value of the absolute zero in degrees Celsius does the calibration yield, and what pressure would be found at the freezing and the boiling points of waters? Okay. So if you understand the principle of the experiments, so you have pressures and the temperatures. Okay. So in this case, you have a pressure at 0.9, which correspond to the minus 70 minus 78.5 degrees centigrades. Okay, so maybe I just need okay, I just maybe write it in this way. Okay, you have 0.9, which is here. So x-axis is temperature, y-axis is pressure. So you have 7.5 with the pressure 0.9. Okay, and then you have 78 with pressure 1.635. Okay, and then you do the expansions. Okay, maybe I'm not doing it. It's better in the scale because this thing should move. Yeah, let's move it in a more realistic. So this is 1.6, 1.8, 1.9 should be about here. Okay, so minus 78.5, 0.9. Okay, and then you do the extrapolations. So this is the linear relations, right? So what you know is that the linear equation y of x equal to slope x plus the constants. Okay, the y-axis is pressure, x-axis is the temperatures. Okay, so you put it back, you put the number you have. So the pressure at the 0.9 equal to slope x as a temperature minus 78.5 plus the constants. So this is the first equation. The second equation is pressure as 1.635, which is slope, x is 78 plus the constants. Okay, so you try to solve by you can 2 minus 1, for example, to get m, and then put m back to 1 or to 2, so you get the constants. Okay. Let's try to do it by yourself. You will get the slope equal to the 4.7 times 10 to the minus 3 atm per degree centigrade, and you will get constants at 1.27 atm. Okay, again, see the units. This side of your unit is pressure, which is atm, so it's clearly C needs to be the atm, okay, which is this one. M needs to be the atm divided by degree centigrade to cancel to this degree centigrade here. Okay. So what pressure would be for the freezing and the boiling point of water? Okay, let's try to do it putting the information you have for the waters. So you should get the answer. Okay. Next, we're talking about the Avogadro numbers. So it's convenient that the expression of the gas in a volume in terms of the number of moles. Okay, this is what people have done. So 1 mole of any substance is the amount of the substance that contain the number of the Avogadro numbers. Okay, so Na equal to 6.023 times 10 to the 23 of the constituent particles. It can be atoms, it can be molecules. Okay, so that's the first definition. So the number of mole, okay, equal to the number of the substance divided by the Avogadro number. So if in that problem it's the number of atoms, so you use the number of atoms. If the equation is the molecules, so you use molecules. Okay. And the number of mole of substance is also related to the mass, to the expression that the number of mole equal to mass divided by the molar mass. Okay, the molar mass is for the chemical element is the atomic mass. Okay, so so the molar mass of the chemical element is the atomic mass. For example, the mass of 1 helium atom is 4U. So this is in the Dalton units view, so the molar mass of helium is basically 4 grams per moles. Okay. Okay. So in the problems, maybe give you as the number of the molecules, number of the atoms, or it can give you as the mass or atomic mass. Okay, so you need to relate these equations correctly. Okay, so don't confuse. We have kindly two definitions. So the number of mole is defined by the number of the atoms or the number of molecules, or to define the number of mole by the atomic mass of the elements. Okay, so we are talking about the ideal gas. An ideal gas is the theoretical gas composed of many random moving point of particles that are not subject to interparticle interactions. Okay, this is the key point of the molar mass. Sorry, not the molar mass, sorry, of the ideal gas. So basically, when you're talking about the ideal gas, so you're talking about the molecules that fly away, and you don't really consider that these two molecular gas will interact with each other. Okay. So from that point of view, it's mean that you have one kind of the ideal gas, because you don't really consider a mass of things, because at the end you consider just how many moles of the ideal gas. Okay, so you don't have two kinds. I mean, in technically the ideal gas is the same. So you have laws that dealing with the ideal gas that will form the what we call the state of gas equations, which is empirical. So it's coming from the experiments. So first we're talking about the Boyle's law. Okay. So in Boyle's law, the temperature is constant. Okay, and the pressure is it's inward proportional to the volume. I'm sorry, just volume. So it's capital V. Okay, so this is Boyle's law. Charles' law is that you get the pressure constants. So the volume is direct proportional to the temperatures. Okay, and the Gay-Lussac law is that you should take the volume as the constants. So the pressure is direct proportional to the temperatures. Okay, so this is three laws that we are using mostly to describe the ideal gas. So we have additional one, which is Avogadro laws, which is at the time that let's say when the temperatures and at the same temperature and pressures, at the same temperatures and pressures, volume of any gas volume of any gas will contain the same number of molecules. Okay, this we will show you in next examples. Okay, so there are basically you have three laws that form the empirical formula for the ideal gas, the state of the equations, state equations of the ideal gas. So Boyle's, when the temperature is constant, pressure is inward proportional to the volume inwards. Okay. Charles' law, when the pressure is constant, the volume is proportional to the temperatures. The Gay-Lussac's law, when the volume is constant, the pressure is proportional to the temperatures. Okay, And then we have the Avogadro numbers, Avogadro's law, when you're talking about the situations that temperature and pressure are the same, not are the same in the state that you have the constant temperature and pressures. The volume of any gas will contain the same number of the molecules. Okay. So finally, if we merge three laws together, Boyce, Charles, and Gay-Lussac, so you get these formulas: PV equal to the nRT. So this formula is empirical, so it's mean that it's come from the experiment. Okay. Okay, so in this case, you see that it's described all the laws all the laws that you have. Okay, so if you keep the pressure constants, it's inverse proportional to the T, which is Charles, right? If you keep the volume constants, P is directly proportional to the temperatures. I'm sorry. If you keep the pressure constant, okay. If you keep the volume constant, so yeah, you have the Gay-Lussac experiments, and if you keep the temperature constants, you have the link between P and V, which is inverse proportional. Okay, because you need to move one to another side, which is gonna be the denominators. So this is Boyle's law. Okay, and the N is the number of moles, is the universal gas constant, so which is 8.314 joules per mole Kelvin. Okay, if we consider a mole of gas at the room temperature as 1 atm, what is the volume? Okay, so the volume in this case is nRT divided by pressures. Okay, so it's 1.9683814. The temperature that used here is Kelvin. Okay, this needs to be Kelvin. Okay, why? Because this thing have the dimension of the joules per mole per Kelvins. Okay, and this one is Kelvin, this one is mole, right? Okay, and then the pressures, which is 1.013 times 10 to the 5 Pascal. Okay, pressure is the force, right? Force is the force per area. So the unit is the Newton per areas. Okay, so the moles cancel, the temperatures cancel. So the unit of volume need to be joule per Newton per areas. Okay, try to solve it. What is the joules? It's the unit of the energies. Okay, what is the newtons? Newton is F, right? F equal to mass time accelerations, right? So mass is kilograms, acceleration is made per second square, for example. So you will see that with the dimensionalities, that joule divided by Newton per area, it's gonna be the unit of the volumes. Okay, the answer is gonna you will get about 24.5 liters. And again, I would say that this is not gas dependent. Okay, so for any gas, any ideal gas we are talking about, at the room temperatures at 1 atm, the volume gonna be the same, 24.5 liters. Okay, so this is the concept. And then at sometimes the ideal gas law is often expressed in terms of the total number of molecules. Okay, because you have the relations as you discuss here. Okay, you have the mole equal to the number of molecules divided by the Avogadro numbers, or the mole equal to the mass divided by the molar mass, which is atomic mass. So you use that knowledge and to try to convert. Okay, so you write the number of mole in terms of the number of the molecule divided by the Avogadro numbers, and then you form the new constant, which is R over Na, and this is what we call the Boltzmann constants. Okay, 1.38 times 10 to the minus 23 joules per Kelvin. Okay, so these two formula, PV equal to the nRT or PV equal to the nkBT, you can use any of them. Just consider consider the problems. Okay, what is providing the problems, you use it properly. Okay, so the PVT diagrams. So you see before we go to the examples, just looking for the PVT diagram. So starting from the equation, we have PV equal to nRT. So if you keep T as a constant, okay, if you keep T as a constant, it means that P times V equal to the constants. Okay, and if you try to plot it, you're gonna got this kind of curve. Okay, and then when the temperature increase, P times V gonna be increased in these directions. Okay, it's not a line, it's not a linear. Okay, P times V equal to the constant. So let's yeah, this is how the diagram should look like. Okay, and then so the line which is the same temperatures. Okay, because in this along one of this line, for example, we are talking about this line, the line that I'm trying to highlight. Okay, the multiplication of P and V become constant, so that's why we call this line as the isotherm line. Okay, isotherm is that the same temperatures. Okay, so next one it's iso short, the iso volume. So we consider in the case that volume is constant. Okay, when the volume is constant, so you plot, so it's like constants equal to the nRT over 3. So we're taking about 1 mole, so this thing become constant. So T divided by V equal to the constants. Or sorry, I should not maybe move. I should just move it back. Let's move constant to 1 point. So it's like volume equal to the constants times T. So the constant is basically here and here. So this is the no, sorry. Let's start. sorry, I think I tried it in the different way, so I just maybe try to make it it should be pressure. So in case of we keep the volume to be constant, so the constants divided by NR, which is also constant, it's multiplied by P equal to the temperatures. Okay. Or we can move these constants to here. Okay, anything time the constants. So you can see that this is the linear equation if you consider pressure in the y-axis and the temperature is in the x-axis. Okay, so you have a linear relations. Okay, and in the line, this line, okay, it's the slope, which is called so we call it the isochore or the isovolume. Okay, and what you should know is that for the increasing of the specific volume, the slope is increasing, and the v is increasing, but the v is basically the denominators, right? So if you write it in a maybe clear way, so pressure equal to the nRT over volume. This is y, this is x. So when the v is increasing, the slope is decreasing. Okay, when v is increasing, slope is decreasing. Okay, so that's why it's moved in these directions. Okay, so the volume increase, the slope decreasing, so the line start to go to the horizontal line, start to become a more horizontal line. Okay. Next, it's about the pressure is constant. Okay. So for the pressure is constant, we're talking about the temperature and the specific volume. So what we can do is we give pressure constants. Yeah, so we can write T equal to the P over N R times V, right? In this case, T is the y-axis, V is the x-axis. Okay, so it's a linear relations, and when the pressure increase, the slope increase. Okay, so when the pressure increase, the slope increase. So this is the trend of the plot. And again, the same as before. So with the same line, it's the same pressures. Okay. We call it the isobar. So since you have basically three parameters, P, V, and T, sometimes people plot it in let's call it the phase in the three different axes. So the volume, the pressures, and the temperatures. Okay, so it's from the plane that describe the state of your materials, of your gas. Okay, and in this plane, if you focus on one direction, for example, if you focus on P and V, you're gonna get the same PV diagrams that you have before. Okay, so it's just forming the 3D plots that describe the state of the gas. Okay, let's go to the last two examples. The first one, if we have the spray that contain a propellant gas at twice atmospheric pressures, and having the volume of this one at certain temperatures, then it's thrown into the open fire. There's a warning that don't do it by yourself. I mean, it's very dangerous. So the temperature of the gas in the can reach very high, 195 degrees centigrade. So there's a pressure inside the can. Assume any change of the volume of the can is negligible. Okay, so you have two states. So you have the first one, which is this pressure, this volume at these temperatures, and then for the second state you have these temperatures at the same volumes. Okay, so what you can do is that from PV equal to the nRT, right, the gas is the same, number of mole is the same, so basically PV over T considered to be the constants. So P1 V1 over T1 equal to P2 V2 over T2. Okay, and then you place the, okay, this is T2, P1 and P2 is the same. Oh, sorry, not pressure, the volume. Oh, and the volume can be negligible change, so that we cancel. Okay, and then you place the pressures P1 and the temperatures. Okay, so you try to put the numbers in, and then what you will get, it's 320 kilopascal. Okay, let's try to do it by yourself. Okay, last examples. I hope you follow me. Last example, the mass of the hot air balloon and its cargo is 200 kilograms. The air outside the temperature of the air outside is 10 degrees centigrade with the, okay, I'm not sure why I type M here, at the 10 degrees centigrade with 101 kilopascal. So the volume of the balloon is 400 square meters. What is the temperature must the air in the balloon be formed before the balloon will lift off? Okay, and they give the the air densities. Okay. To work on these questions, you need to have imaginations. So you need your Newtonian mechanics, basic things, and the fluids mechanics. Okay. So let's imagine before balloon is lift off. So you have the balloons, right? So you have the hot airs here. Okay, this is the land. Okay. So before it lift off, it's mean that this balloon is still in the situation that it doesn't move, right? So the sigma f should equal to zeros. Okay. So what is the sigma f? So they have the weight of the balloon. Okay, the weight of the balloons, the weight of the air, right? Because in the question it said that the mass of the hot air balloon and its cargo is 200. But not include the air inside. Okay. Sorry, just confused the words. The hot air balloon mean the whole balloons, you know, but not the air that you fill into this in this one. Okay. And then you need to have the buoyant force to raise you up, because in this case you have only something to pull you down, right? Okay, you have the weight only, so you can go up if you have the force. This is a buoyant force that can raise you up. So you have the buoyant force here. So it means that to equate the equation, you have the buoyant force minus the weight of the air inside balloon minus the weight of the balloon itself equal to the zeros. Okay. Yeah. So what you have to do is just place the information to the equations. So the weight of balloon is clearly its mass of the balloon times g's. Okay. The weight of the air is mass of the air times g's. The same, right? The mass of the air, what exactly it is? It has the air densities. Okay. So it's rho times v. Okay. Right? Because the problem is it gives you that the air density is at 10 degrees centigrade is 1.244 kilograms per cubic meters. Okay, and then the buoyant force is let's say the volumes that the volume of the balloon which is replaced by the air. Okay, so in this case, this buoyant force is that the rho of the outside times v, times g is times v. Okay, the rho inside. Okay. Okay, you remember this one? Okay, so basically when you have the balls and you put the ball to the tank of the waters, and you would like to calculate the buoyant force of the ball, so you take the volume of the balls but the density of the waters instead. So if this ball is displaced to the water, displaced by the water, so to calculate that, you take the volume of something you put in the waters, but for the density you use the density of the water instead. Okay. So in this case, you can calculate it's equal to 0. So we can cancel g first. So at the end we get rho out minus rho in times v, right, equal to the mass of the balloons. Okay, and the question is that to what temperature must the air in the balloon be warm before the balloon will lift off? Okay, we manage the first sections, the first parts. So we're gonna do next to calculate the temperatures. So in this case, we're gonna use the ideal gas law to do that. So what to do? It's basically consider the ideal gas laws. So you have, maybe I change the colors. Sorry, maybe I just move. Sorry, I have to move these formulas a bit, so that we have more space. Okay. let's change to the black one. So consider the ideal gas law. PV equal to the nRT. Okay. Right. So what we can do is basically this can be mass divided by something. Yeah, right. So we let's make V divided by N equal to the R T, no, sorry. I would just want to do, I'm sorry, P divided by R and T equal to the N divided by the volume. Okay. So this term, it's in the it's the volume, right? So it's maybe not the right, I mean exactly right. I mean you can just, okay, the n equal to the mass by something, okay, and that something gonna be absorbed it to become one of the constants in your formula. Okay. You can write it if the mole it's mass divided by some numbers, and you know that's numbers, it's gonna be constants. So it's the same here. So we are talking about the pressures which is under the air. So it's in these pressures, and the R is constant. So this thing is also constant. Okay. So it's mean in this case rho times T gonna be constants. Okay, we don't care about the constant, so that's why I don't really write n to the real exact formula of the mass divided by the numbers. Okay, just to give the concept that, okay, when things are constants, we just merge it together and call it that it's a constant. So in this formula, rho T equal to the constants. So which means rho in T in equal to the rho out T out. Okay. Right. So at the end, what you're gonna get is that what should be done, you have rho out minus rho in equal to this one, right? Okay, so you have the first equation, this is the second equation. So for the second equation, you have rho out sorry, T out, just a second. Sorry, I should make it easy. Okay. What to do is basically, okay, so from this line you have take rho out, okay, you have rho in over rho out equal to the T out over T in, right? Use this one, put back to the first equations, right? It's become rho out 1 minus rho in over rho out equal to mass of the balloons times V. Okay, so you have already that rho in over rho out is T out or T in. Okay, and then you can calculate. Okay, the T out is basically 10 degrees centigrade, so 283 kelvins. Mass of the balloon you already know, the volume you already know. Okay, and the density of the air outside is known. Okay, so finally you can calculate T in. You will get 470 kelvins as the answer. Sorry, it's I write it as a mess a little bit. So I would propose that you try to review that by yourself again, and I may try to explain it well in the tutorial class again and with more examples of these chapters. Okay, so I think we are done with the temperatures and the zero law of the thermodynamics. So to give you a picture of what we're gonna discuss next is that when you're talking about the air, okay, in these chapters we are talking about the macroscopics. So something that you measure, for example, the temperature, the pressure, the volume. So you're talking about overall of the systems. And the next section, which is the kinetic theory of gas, is basically you're looking in the microscopic. Okay, so we are not talking about the air overall, but we are talking about the air molecules. Okay, so that molecule is moving, so they have the kinetic energies and they have the potential energies. It's go hit to the wall, what's going to happen? Okay, and what's related quantities that we are talking about. But the most important thing is that two worlds need to meet at some point, right? Because it's the same system. So whatever temperature is described in the macroscopic pictures, it needs to be the same temperatures that described in the microscopic pictures. Okay, so that is the goal of the next sections. Okay, I think we are done for this one, and the video for the kinetic theory of gas will be uploaded also later. I hope that's to be this afternoon. Thank you very much, and see you in the next video.